Okay, this video is part of the playlist that deals directly with chemical equilibrium. However, it is the first video in the playlist where I demonstrate how to do equilibrium calculations. And what we're going to do in this video is start by calculating the equilibrium concentration of a product when we're given equilibrium pressures of the other components in the reaction. So let's start by actually reading the question. So we're given the following chemical equation where we have two NOs that react with bromine to produce two NOBRs. And the question is stated the following way. Nitric oxide, which is NO, is combined with bromine at 25 degrees centigrade and allowed to reach equilibrium, producing some NOBR. At equilibrium, the partial pressure of NO is 0.142 atmospheres and the partial pressure of bromine is 0.166 atmospheres. Find the partial pressure of NOBR at equilibrium. The Kp for this reaction is 28.4. So what we're going to do to start is by first rewriting the chemical equation, because we're going to need to utilize what we call an ICE table for this. And an ICE table ICE is the abbreviation for initial change equilibrium, and I call an ICE table the box. My students know this as the box. So the first thing that we're going to do is we're going to write the balanced chemical equation. And then we're going to start to translate in the information. All right, and I'm going to rewrite my Kp here so I have it right in front of me where I can see it. Now, what we're going to do first is I want to try and lay the background for this problem. All right, you're told that we have the equilibrium pressures of the NO and of the Br2. The NOBR is unknown. But what I want to do here is try to lay the foundation for, in terms of how this problem was written, what has actually occurred. So we're going to produce the ICE table for this. So what I want to do is establish what occurred initially before any reaction. And before any reaction, even though it's not stated in this problem, we had some partial pressure, initial partial pressure of NO, which I'm just going to call A. And we would have had a partial pressure of Br2, which I'm going to call B. And prior to any chemical reaction, there was no NOBR, so we'll put a 0 there for that. Now, in the process of coming to equilibrium, and normally the way I list that is in my ICE table, in my box, is by just using the word after. So in order to reach equilibrium, the initial concentration of NO would have had to have decreased based on its stoichiometry. So it would have decreased by a factor of 2x. The 2 representing the fact that there's a coefficient of 2 in the balanced equation. The bromine, by the same token, would decrease by a value of x, since the coefficient here is only 1. And the NOBR would have been formed at a rate of 2x. 2x. Now, going back to the problem itself, we're told that at equilibrium, the partial pressure of NO gas is 0.142 atmospheres. So what you need to realize is that after equilibrium is reached, this difference of A minus 2x is equal to 0.142 atmospheres. Similarly, the difference B minus x is equal to the equilibrium partial pressure of 0.166 atmospheres of Br2. And the equilibrium pressure of NOBr is simply 2x. Now, we're ready to set up our equilibrium expression. So the first thing I'm going to do is write down my Kp. And this is equal to 28.4. And this is going to be equal now to the equilibrium expression, which is going to be the partial pressure of NOBr raised to the second power. So, and I think I'm going to go ahead to make sure that I'm absolutely clear here. I'll go ahead and write this in without numbers first. So, partial pressure NOBr quantity squared over the partial pressure of NO gas, also squared, times the partial pressure of Br2 raised to the first power. Okay, and now I'm going to go ahead and plug in my numbers. So the 2x is going to be in the parentheses. This is quantity squared. All right, and then the partial pressure of NO is 0.142 atmospheres, quantity squared, and the partial pressure of the Br2 is 0.166, quantity raised to the first power. So we're going to have, doing the algebra now, we're going to have 28.4, and I'm going to go ahead and simplify the 0.142. In other words, I'm going to go ahead and square it out. And when I do that, it's going to be 0.020164. All right, and that will be times 0.166, where the whole thing is equal to 4x squared. All right, now simplifying again, my 4x squared is going to be equal to, and hopefully as you follow me through this video, the best thing to do is have out your calculator and be running the calculations yourself. All right, and you can pause the video anywhere you need to in order to keep up. In any case, the 4x squared is going to be equal to the 0.09506. And then we're going to divide both sides by 4. So x squared is going to equal 0.02376. And then I'm going to take the square root of both sides. So my x is going to be equal to the square root of this value, so 0.023765, where x is 0.154. Now, to find the partial pressure of the NOBr, this is going to equal 2 times this value, which is equal to 0.308 atmins for the NOBr. Now, I highly recommend that you double check your work. So, and what I mean by that is that we're going to go ahead now and we're going to take this value along with the other values, and we're going to plug them into our Kp expression and solve for the value and make sure that it equals, it should be very close to 28.4. So this is going to equal, Kp is going to equal 0.308 quantity squared over 0.142 quantity squared times 0.166 quantity raised to the first power, and when I run this I get 28.3. So you can see that our Kp here matches very well the Kp that we were given in the problem. All right, now one last word of advice. I think it's really important to think completely through these problems. Even a problem like this one where they don't give you the initial concentrations, it's important for you to realize that somewhere in the beginning you had to set the reaction up in a reaction flask, and the reaction had to come to equilibrium. Now, in these initial examples I'm going to run through, we're going to start out with easy problems from the point of view that you're normally not going to be given the equilibrium pressures of the product. So when we set up our ICE table, the reaction is going to be shifting to the right. And you'll have to think through the process the way I laid it out here. And I think with that, I'm going to go ahead and close this particular video.